Welcome to our explainer. Have you ever stopped to think what the sizzle of a steak, the rust on an old car, and the very act of breathing all have in common? Well, today we're going to decode the hidden chemical reactions that connect them all. Reactions that literally shape our world every single day. Yeah, I know. They seem completely different, right? But believe it or not, they all share a fundamental secret. They are all chemical reactions. I mean, think about it. From the food on our plate to the air we breathe, chemical changes are happening constantly, transforming one substance into something completely new. So, how do we even begin to understand the secret language of change? Well, the first step is knowing when a reaction is even happening. You have to look for clues, almost like a detective showing up at a crime scene. So, let's look at the evidence. Take this experiment with a magnesium ribbon. When you burn it, it goes off with this dazzling white flame and turns into a totally different white powder. That's magnesium oxide. Or what about this one? You add some zinc to acid, and you get bubbles fizzing up, and if you touch the container, it's actually getting warm. That's another dead giveaway. So, here's the crucial takeaway. These observations, a change in state, a new color, bubbles, a shift in temperature, these are our telltale signs that a chemical reaction has definitely happened. Okay, so now that we can spot a reaction, how in the world do we talk about it? Well, scientists needed a shorthand, right? A universal language to communicate these changes precisely without writing a novel each time. Let's see how this works. You can start with a really long sentence describing what happened. Then you can shorten that to a simple word equation, and finally, you use the chemical formulas, which makes it incredibly concise and powerful. In this new language, the ingredients you start with are called reactants, and the final result is the product. And that little arrow just shows you the direction of the change. But here's the thing. Just writing it down isn't the whole story. There's a really big rule you have to follow. In fact, that last equation we saw, Mg plus O2 goes to MgO, well, it's got a huge problem. As it's written, it actually violates one of the most fundamental laws of the entire universe. And that law is the law of conservation of mass. It basically means you can't just create or destroy atoms out of thin air. You can only rearrange them. This isn't just a rule for chemistry. It's a core principle for, everything. So, an equation must be balanced. That means the number of atoms for each element has to be exactly the same on both sides. We make this happen by adding coefficients. Those are the big numbers out front, to make sure the atomic accounting is perfect. It's like balancing a checkbook for the universe. Now, once you get the hang of balancing equations, you start to notice something really cool. Most reactions aren't random. They actually fall into a few common genres or families, and each one has its own signature pattern. First up, you've got your combination reaction. This one's super easy to spot. It's basically two or more things coming together to form a brand new single thing. A plus B gives you AB. Simple as that. And the exact opposite of that is a decomposition reaction. This is more like a breakup, where one complex thing splits apart into multiple, simpler parts. Then, things get a little more interesting with the displacement reaction. This is where a more reactive element basically cuts in and swaps places with a less reactive one in a compound. And you can literally see this happen. Check this out. An iron nail gets put into this blue solution, and you can see it getting coated with copper. That's visual proof that the displacement reaction happened right before our eyes. The iron literally kicked the copper out. And finally, you have the double displacement reaction. In this one, it's like two couples on a dance floor just swapping partners, creating two entirely new pairs. Everybody switches. And a really common result of this is the formation of a precipitate. That's basically a solid substance that suddenly appears in the liquid, almost like magic. It just pops into existence. So, why does speaking this chemical language even matter? I mean, who cares? Well, because one specific type of reaction, oxidation, is happening all around us, all the time, for better and for worse. So in really simple terms, oxidation is when a substance gains oxygen and reduction is when it loses oxygen. And the key thing here is they always happen together. They're a package deal. Now, this process is responsible for some pretty serious problems,
like the corrosion that damages bridges and cars, or the rancidity that makes our food go bad and taste awful. But understanding oxidation is the key to preventing it. Ever wonder why chip bags are all puffed up? It's because manufacturers flush those bags with nitrogen gas. It pushes out the oxygen to keep your snacks fresh and stops them from going rancid. So by recognizing the clues, understanding the language, and seeing the patterns, you can now see the world just like a chemist does, as a place of constant, incredible, and fascinating transformation.